Welcome to the Curious Voyager. It's lovely to have you here wherever you are tonight. Maybe you're lying in the dark with the blanket pulled up to your chin. Maybe there's a lamp still on somewhere across the room, throwing a soft little pool of light on the ceiling. Maybe you're on a train, or a couch, or a bed that isn't quite yours. Wherever you are, and whatever hour it's reached in your corner of the world, you've found your way here. And I'm glad. Settle in. There's nothing you need to do now. Nothing to hold on to. Nothing to solve. You can let your eyes close whenever they want to. The story will keep going, softly. And it'll still be here if you drift off before the end. And before we begin, if you enjoy these slow journeys and want more of them, a quiet like and a subscribe really do help this sleepy little channel keep going. Small creators like me rely on it more than you'd think. And to those of you already subscribed, already part of the voyage, thank you. Truly tell me, before you drift, where in the world are you listening from tonight? And what time has it gotten to where you are? I always love to imagine all of you scattered across the dark side of the planet, all quietly awake together. Now let me tell you something strange to fall asleep to. For 30 years, some of the smartest people alive quietly believed that a man at the bottom of a gold mine had made a mistake. Not a wild man, not a careless one. A patient, meticulous chemist, nearly a mile underground in South Dakota, counting something almost impossibly small. He kept getting the same answer year after year, and the answer was that 2/3 of the tiny particles streaming out of the center of the sun were somehow not arriving. They were leaving the sun. They just weren't showing up in his tank. And the response of physics for 3 decades was more or less a gentle, collective shrug in his direction. He must be miscounting. Or the other fellow, the one who'd worked out how many particles the sun ought to be making, his model of the sun must be off. The sun must be a little cooler than we thought, or built a little differently on the inside. Anything, really, anything but the third possibility. Because the third possibility was that both of those men were right, exactly right, the whole time, and the thing that was wrong wasn't the counter, and it wasn't the sun. The thing that was wrong was the most successful theory in the history of science. That's where we're headed tonight. Slowly, no rush at all. It's a story about 2/3 of the sun's ghosts going missing, and the man everyone assumed had simply lost count, and the 30 years it took to realize the ghosts had never gone missing at all. They arrived right on schedule, in exactly the number predicted. They just quietly changed into something his tank was built not to see. And here's the part I love most, the part that makes it worth a whole long night. The feat at the heart of it. To do what this man did, he had to reach into a tank the size of a swimming pool, filled with hundreds of thousands of litres of fluid, and pull out a few dozen individual atoms. Not a few dozen grams. Not a few dozen drops. A few dozen atoms. You could count them on your fingers and toes, sifted out of something like 1,000 billion of their neighbours, every few weeks, a mile underground. And then he had to prove to a sceptical world that he really could do that, before anyone would even take his strange results seriously. I told you it was strange. Don't worry about holding all of it. The names, the numbers, they'll come around again and again through the night, and you'll meet them gently, one at a time. I'll try not to make this so interesting it keeps you awake, but if it does, well, at least you'll have learned something. A fair trade, I think. So let's go back, way back, before the gold mine, before the sun even enters into it. Because to understand why 2/3 of anything could go missing, you first have to understand how anyone came to expect the particles to be there at all. And that thread begins with a physicist who invented one of these particles almost against his own will, and who then felt quietly guilty about it for years, because he was certain he'd dreamed up something that could never, ever be found. His name was Wolfgang Pauli. Picture, if you like, the world of physics around the year 1930. It's a small world in a way. A few hundred people, scattered across Europe mostly, who really understand what's happening at the frontier. They write each other letters. They gather in little conferences in university towns. They know each other's handwriting. And they have a problem. A quiet, nagging, embarrassing problem that won't go away. The problem lives inside something called beta decay. Now that sounds technical, so let me set it down gently. There are certain atoms, certain kinds of atomic nuclei, that are unstable, restless, and every so often one of them will spit out a tiny particle, an electron, and in doing so transform into a slightly different kind of atom. That's beta decay. A nucleus letting go of a little burst of energy in the form of a flung-out electron. It's a bit like a person who's holding too much and finally sets a package down to steady themselves. There's a before and there's an after, and the difference between them is a fixed, known amount of energy. That's the whole point. Energy is supposed to be conserved. It's one of the deepest, most trusted rules we have, that the books always balance. Whatever energy goes missing from here has to show up over there. It can't just vanish. So here's what physicists expected. If the nucleus lets go of a fixed amount of energy, and that energy goes into the flung-out electron, then every electron from that same kind of decay ought to come flying out with the same energy. The same speed, more or less. Like dropping identical balls from the identical height, they should all hit the ground, going the same pace. But that's not what happened. Not at all. When they measured the electrons coming out of beta decay, they found a whole smear of energies. A continuous spectrum, they called it, which just means a smooth range, from almost nothing all the way up to the maximum. Some electrons came out slow, some came out fast. Most were somewhere in between. And that maximum, that fastest possible electron, that was the energy the books said every electron should have had. Instead, almost all of them came out with less. Sometimes far less. So where was the missing energy going? Sit with how uncomfortable that is for a moment. You have a rule you trust more than almost anything, that energy is never created and never destroyed, that the accounts always balance. And here's a perfectly ordinary process, happening in ordinary matter, where the accounts flatly refuse to balance. Energy is walking out of the room and not arriving anywhere you can find it. Night after night, experiment after experiment, the same shortfall. And some very serious people started to wonder something almost heretical. They started to wonder whether energy conservation itself might simply break down inside the atom. Whether, at this tiny scale, the sacred rule just didn't hold. Chief among them was Niels Bohr, one of the towering figures of the whole field, a man whose instincts had been right about so much, and Bohr was genuinely willing to entertain the idea. To let energy conservation go. To say, perhaps down here, in the heart of the atom, the books are allowed to not balance. That's how bad the problem was. A physicist of Bohr's stature was ready to give up one of the crown jewels of physics to make sense of it. And this is where Pauli comes in, and where his desperation comes in, because he himself would call his answer a desperate one. Pauli couldn't stomach abandoning conservation of energy. To him it was too precious, too load-bearing. Pull that stone out, and the whole cathedral might come down. So he reached for the other option, and the other option was almost embarrassing in its simplicity. What if the energy isn't missing at all? What if it's being carried off, quietly, invisibly, by a second particle? A particle so shy, so faint, so unwilling to interact with anything that it slips out of the experiment unseen, taking its share of the energy with it and telling no one? Then the electron gets whatever's left over, which is why you'd see that whole smear of electron energies. Sometimes the invisible particle takes a lot, and the electron gets a little. Sometimes it takes a little, and the electron gets a lot. The two of them split the fixed amount between them in every possible proportion, and the books balance perfectly. You just can't see one half of the ledger. It's a lovely idea. It's also, at the time, an act of near faith. Because Pauli was proposing a particle that nobody had ever detected, that carried no electric charge, so you couldn't push or pull it with magnets, and that seemed to pass through matter as though matter weren't even there. He was, in effect, saving the most trusted law in physics by inventing a brand new invisible thing to hide the discrepancy inside. He knew exactly how that looked. And so, on the 4th of December 1930, Pauli did something rather wonderful. There was a physics gathering happening in the German town of Tübingen, a meeting on radioactivity, and Pauli was invited. But Pauli didn't go. He had, of all things, a ball to attend in Zurich. A dance. So instead of showing up to defend his strange idea in person, he sent a letter to be read aloud to the assembled physicists. And the letter opens with one of the most charming salutations in the history of science. He addresses them as "Dear radioactive ladies and gentlemen." Imagine that being read out to a room full of serious scientists. "Dear radioactive ladies and gentlemen." And in this letter he lays out his desperate remedy that's genuinely close to how he framed it, a way out born of desperation, Verzweifelter Ausweg in his own German, a desperate escape route for saving the conservation of energy. He proposes his shy, neutral, nearly undetectable particle, and he half apologizes for it as he does. He knows it's a big thing to ask, a particle you can't see, invented to explain energy you can't find. He even frets, in his letter, that he may have done something no honest physicist should do, proposed something that can never be tested, never confirmed, never caught. He's asking the cleverer experimenters in the room to please try to find it anyway. He gave it a name, too, in that first letter. He called it the neutron, the neutral one, which was a perfectly good name for about 2 years. Because in 1932, a physicist named James Chadwick, working in England, discovered a real particle sitting inside the atomic nucleus. A heavy, neutral particle, one of the fundamental building blocks that make up the cores of atoms alongside the proton. And that particle, quite reasonably, got the name neutron, the one we still use today. The neutron in every chemistry class, in every diagram of an atom you've ever seen. That was Chadwick's. So Pauli's little invented ghost suddenly had no name, because the good name had been taken by something real and rather more substantial, which is where a third figure steps softly into the story and gives the ghost the name it has carried ever since. His name was Enrico Fermi, an Italian physicist, one of the great minds of the century, a man who could do both the deep theory and the hands-on experiment, which is rarer than you'd think. And Fermi, being Italian, gave Pauli's particle an Italian name, and a rather sweet one. Chadwick's heavy neutral particle was the neutron, and in Italian that word carries a sense of the big neutral one. So Fermi looked at Pauli's tiny, feather-light, barely there version and called it the neutrino. The little neutral one. That's all it means. The neutron is the big neutral one, the neutrino is the little neutral one, the diminutive, the small shy cousin. Neutrino, and the name was so right, so affectionate and fitting, that it stuck completely and forever. But Fermi did far more than name it. He took Pauli's desperate hunch, this invisible particle carrying off the missing energy, and he built it into a proper quantitative theory. A real piece of mathematics that described exactly how beta decay works, with the neutrino woven right into the heart of it. This was around 1933 and 1934. And his theory was, in time, a triumph. It explained the shape of that smeared electron spectrum. It made predictions. It became one of the foundations of how we understand the forces inside the atom. And do you know what happened when Fermi first tried to publish it? The journal Nature, one of the most prestigious scientific journals in the world, then as now, rejected it, turned it down. And the reason they gave, or the reason that's come down to us, is almost painful to hear with hindsight. They said it was too remote from reality, too speculative, too far from anything real to be worth printing. Too remote from reality. A theory that would, decades later, be confirmed to staggering precision and underpin a whole branch of physics, sent back with a note that it was too unreal to bother with. I find something oddly comforting in that, actually, something to carry into sleep. The idea that even the greatest journals, even the sharpest editors, can look straight at something true and important, and simply not see it yet. That being right and being believed are two entirely different things, often separated by years. Hold that thought loosely. It's going to matter a great deal later tonight, when a certain man in a certain mine keeps getting an answer nobody wants to believe. So now we have a particle. We have a name for it, neutrino, the little neutral one. We have a beautiful theory built around it by Fermi. There's just one small problem, and it's the problem Pauli fretted about in his very first letter. Nobody had ever seen one. And it wasn't for lack of trying, exactly. It was that the thing seemed almost designed to be invisible. Remember why Pauli invented it in the first place. He needed a particle that could slip out of an experiment completely unnoticed, carrying energy away without leaving a trace. That's the whole reason it solved the problem. But that same shyness is precisely what makes it so maddening to catch. A neutrino has no electric charge, so you can't grab it with electric or magnetic fields the way you can steer an electron. And it barely interacts with ordinary matter at all. Barely. Let me try to give you a feel for how shy this particle is, because it's genuinely hard to hold in your mind. A neutrino can pass straight through solid matter as though the matter simply isn't there. Not through a sheet of paper, not through a wall, through the entire Earth. A neutrino can fly in one side of our planet and out the other, through all those thousands of miles of rock and iron and molten core, and never so much as brush against a single atom on the way. Most of them do exactly that, all the time. It's a bit like imagine trying to catch a single, particular ghost by holding up a butterfly net. Except the ghost isn't just good at slipping past the net. The ghost drifts straight through the net, and through your arm, and through the whole house, and out into the night, and never once notices you were there. That's what Pauli had invented. That's what he'd felt guilty about. He was reported to have said, more or less, that he had done a terrible thing. He had postulated a particle that could not be detected. To a physicist, that's almost a sin. Science lives on testing, on checking, on going out and finding the thing, and Pauli feared he'd dreamed up something forever beyond the reach of any experiment, a solution you had to simply take on faith, a ghost you could believe in but never shake hands with. For 26 years, he was more or less right. 26 years. Sit with that stretch of time in the dark for a moment. From 1930, when he sent his letter to the radioactive ladies and gentlemen, more than a quarter of a century would pass, through the whole of the 1930s, through the Second World War, through the enormous upheavals that came with it and after it, and in all that time, nobody could catch a neutrino. The particle was accepted, more or less. The theory worked. Physicists used the neutrino in their calculations, and it behaved. But it remained a thing believed in rather than a thing seen. A guest whose coat you could feel the draft of, but whom you'd never actually met. And then, in the 1950s, two men decided to try to meet it. Their names were Clyde Cowan and Frederick Reynis, and they understood something clever about how you might, just possibly, catch the uncatchable. The trick isn't to make your detector better at grabbing neutrinos, you can't. They slip through everything. The trick is to have so unimaginably many neutrinos streaming through your detector that, purely by chance, once in a great while, one of them happens to score a direct hit on an atom and leave a trace. If a butterfly net can only catch one ghost in a trillion, then your only hope is to have trillions upon trillions of ghosts pouring through it every second and wait for the rare, lucky snag. So where do you find an absolute flood of neutrinos? In the 1950s, the answer was new and a little chilling and very much of its time. A nuclear reactor. The nuclear reactors being built in that era were, as a byproduct of all that radioactive activity inside them, ferocious fountains of neutrinos, pouring out vast numbers of them every second. So Cowan and Reynis took their experiment to a reactor at the Savannah River plant in South Carolina. And they gave the whole endeavour a name that tells you exactly how they thought of the thing they were hunting. They called it Project Poltergeist. A poltergeist, a ghost that you can't see, but that you can just barely catch acting on the world. That was the neutrino to them, invisible itself, but maybe, just maybe, betrayed by the faint mark it leaves behind. And the mark they went looking for came from a very particular reaction. One that runs, in a sense, in the opposite direction from the beta decay that started this whole story. It's often called inverse beta decay, where ordinary beta decay had a nucleus spitting out an electron and a neutrino. This reverse process has an incoming neutrino, technically an antineutrino, the antimatter partner, from the reactor, strike a proton and turn it into a neutron while flinging out a little burst of the antimatter twin of the electron, a positron. Now here's the beautiful part, the part that made it catchable. That reaction leaves not one but two distinct little flashes of light, in a very particular 1-2 pattern, separated by a tiny sliver of time. First, the positron appears and quickly annihilates, giving off a flash. Then, a heartbeat later, the freshly made neutron gets absorbed by an atom in the detector and gives off a second, different flash. And Cowan and Reynis built their detector, great tanks of water laced with cadmium chloride to help catch those neutrons, precisely to watch for that unmistakable 1-2 signature. Flash, then flash, in just the right rhythm. Any single flash could be all sorts of things: background noise, cosmic rays, ordinary radioactivity. But that specific double flash, in that specific pattern, with that specific timing, that could only be a neutrino caught at last in the act. And in 1956, after all the patient work, watching and waiting for the poltergeist to knock, they saw it. The pattern, again and again, exactly as predicted. 26 years after Pauli sat down to write his apologetic letter to a room he didn't attend, 26 years after he confessed he might have invented something no one could ever find, someone had found it. The ghost was real, the shy little neutral one, the desperate remedy, the particle too remote from reality. It was there, it had always been there, and now, finally, they'd shaken its hand. There's a small human detail here that I've always loved, and it's the perfect place to let this first part of our journey come to rest. Cowan and Rains knew whose ghost this really was. They knew that whatever their names on the paper, this particle belonged, in a sense, to the man who had dreamed it up in desperation a quarter-century before, and then quietly carried the guilt of it. So they sent Wolfgang Pauli a telegram, a short message across the world to tell him the news that the particle he'd invented to save the conservation of energy, the one he'd feared could never be detected, had been detected. It was real, and Pauli, by every account, was overjoyed. Vindicated, the desperate remedy had turned out to be no mistake and no sin, but a true thing about the world, hiding just out of sight for 26 years, waiting for someone patient enough and clever enough to build a net large enough to snag it. He is said to have celebrated with champagne. After all that time, after all that doubt, the ghost had come in from the cold. Not all of the story ends in celebration, though, and it's worth honouring the ones who didn't get to stay for the reward. Clyde Cowan, one of the two men who caught that first neutrino at Savannah River, died in 1974. And the great prizes of science, the Nobel Prizes, are only ever given to the living. They aren't awarded after death. So when the Nobel Prize in Physics finally came, in 1995, decades after that first double flash in South Carolina, it went to Frederick Rains alone for the detection of the neutrino. Cowan wasn't there to share it. It's a quiet ache that runs all through this story, actually, the long, long gap between doing the work and being honoured for it, and how often the honour arrives too late for someone. We'll meet that ache again before the night is through, more than once. So here is where we've come to as you lie there in the dark. We have a particle that was born out of pure desperation, invented by Pauli in 1930 to keep the books of the universe balanced, rather than let the sacred law of energy conservation quietly collapse. We have it named by Fermi, the little neutral one, the neutrino, and built into a real theory that a great journal once waved away as too remote from reality. We have it hiding, uncatchable, for 26 years, a ghost believed in but never seen. And we have it caught at last, in 1956, beside a reactor in South Carolina, betrayed by a faint 1-2 flash, Project Poltergeist. The telegram to Pauli, the champagne. The neutrino is real. That much, by the late 1950s, is settled. But everything so far has been the neutrinos we make, or the ones that come pouring out of a reactor built by human hands. And the real story, the one this whole long night is truly about, the 2/3 that went missing, the man everyone assumed had miscounted. The crack in the most successful theory ever written, that story begins when someone stops looking at reactors and starts looking up. When someone decides to try and catch, not the neutrinos we make down here, but the ones streaming out of the heart of the sun itself, 93 million miles away, born in the same nuclear fire that gives us daylight. Because if you could count those, If you could actually catch the neutrinos arriving from the center of the sun and measure how many there were, then you'd be doing something extraordinary. You'd be taking the pulse of the sun's core directly. Not its surface, not its light, which takes ages to crawl up from the center, but its very heart, right now, as it burns. The neutrinos fly straight out of the core and reach us in minutes, carrying a true and immediate message from a place no telescope could ever see. And so, in a gold mine in South Dakota, nearly a mile underground, a patient chemist began to fill an enormous tank with dry cleaning fluid and set out to count the ghosts of the sun. His name was Ray Davis. And that, the tank, the mine, the impossible arithmetic of pulling a few dozen atoms out of an ocean of them, and the strange, stubborn, unwelcome number that came back, is where we'll go next. But not yet. There's no hurry at all. Let the picture settle for now, Pauli at his ball in Zurich, while his letter is read aloud to the radioactive ladies and gentlemen. Fermi, giving the little ghost its gentle name, 26 long years of silence, and then, at last, a poltergeist knocking twice in the dark beside a reactor, and an old physicist raising a glass because the thing he thought could never be found had finally, quietly, arrived. Rest here a while. The sun and its missing ghosts will keep. We'll go down into the mine together in a little while, slowly, when you're ready. So, let's go down into the mine. The year is somewhere in the early 1960s, and Ray Davis has an idea that most of his colleagues regard as either very brave or very foolish, and possibly both at once. Davis is a chemist, not a physicist, a chemist, working at Brookhaven National Laboratory out on Long Island, in New York. He is a quiet man, by most accounts. Patient in the way that only people who genuinely love what they do tend to be patient. And what he loves, more than almost anything, is the problem of measuring things that are almost impossibly small. Things that by all ordinary human reckoning should not be measurable at all. He has been thinking about neutrinos for years already. Not as a theorist, he isn't interested in the mathematics of the particle in the abstract, but as an experimentalist, as a man who wants to build the thing that will actually catch one. Or many, or, as he is starting to understand, not nearly as many as the theory predicts. But we're getting ahead of ourselves. For now, Davis has a problem, and a plan, and the plan is one of the most peculiar in the history of science. Here is what he knows. The sun is powered by nuclear fusion. At its core, a place 12 or 13,000 kilometres across, hotter than you could reasonably imagine, compressed to a density many times that of lead, hydrogen nuclei are being fused together into helium, step by step, in a chain of reactions that releases an enormous amount of energy. And that energy is what you feel when the sun falls on your face in the morning. The light takes tens of thousands of years to fight its way up through the dense plasma of the solar interior, bouncing and scattering and losing its way until it finally reaches the surface and flies off into space. By the time it touches you, it is carrying a message from a nuclear fire that burned long before you were born. But the neutrinos are different. The neutrinos are produced in those fusion reactions, electron neutrinos specifically, born from particular steps in the chain. And they do not scatter. They do not bounce. They just leave. They shoot straight out of the core, and 8 minutes later they pass through the Earth as if it were not there, and most of them keep going, out into the dark of the solar system and beyond, never having touched a thing. This means something remarkable. If you could count the neutrinos arriving from the sun, you would not be measuring the sun's past. You would be measuring its present. The very moment of burning, the core as it is right now, carried to you on particles that left minutes ago and flew through everything without stopping. No telescope in the universe can tell you that. The light from the sun's surface is old information. The neutrinos are a live feed. And John Bahcall, a young theoretical astrophysicist who would spend much of his career at the Institute for Advanced Study in Princeton, had been working out exactly how many of those neutrinos the sun ought to be sending. He built what came to be called the Standard Solar Model, a detailed mathematical portrait of the solar interior, specifying its temperature and density and composition, and predicting from those properties how often each step of the fusion chain should occur, and therefore how many electron neutrinos per second should be arriving at the Earth. He and Davis had begun talking to each other, which was itself a slightly unusual collaboration, the theorist and the chemist, but they shared a belief that the measurement was possible, and that it would tell them something important. What Davis proposed to build was this: a very large tank, underground, to shield it from the constant rain of cosmic rays that would otherwise overwhelm any signal, filled with a particular liquid that would very occasionally react with an incoming electron neutrino, and sensitive enough to detect that reaction even though it would happen, at most once or twice a day in the entire tank. The liquid he chose was tetrachloroethylene. You may know it better by another name. It is the solvent used in dry cleaning. You can buy it by the tanker load. It is cheap, it is stable, it does not catch fire, and, crucially, it is extraordinarily rich in chlorine. And chlorine is the key. The reaction Davis was looking for works like this. An electron neutrino arrives, one of the ghostly particles flying out from the sun's core, and very occasionally, with a probability that would make even patient people despair, it strikes a nucleus of chlorine-37 inside the liquid. When that happens, the neutrino is absorbed and the chlorine-37 is transformed into argon-37. An electron is kicked out in the process. The chlorine becomes argon. Just for a moment, we'll come back to what happens next. Just hold that image. A neutrino from the center of the sun, traveling 8 minutes through space, passes through the Earth, passes through nearly a mile of solid rock, and strikes one particular nucleus in one particular molecule of dry cleaning fluid. And that nucleus is quietly, silently changed into something else. That's the reaction. _E plus chlorine-37 becomes argon-37 plus an electron. Quiet, subtle, and, in the world of particle physics, almost heartbreakingly rare. There is a catch, though, and it matters a great deal, though we will only fully understand why it matters much later. The reaction has a threshold. It takes a certain minimum amount of energy to trigger it, 0.844 million electron volts, which is written as 0.814 MeV. And most of the neutrinos the sun produces don't carry that much energy. The dominant source of solar neutrinos, the proton-proton chain reaction at the heart of the fusion process, produces neutrinos with lower energies than the threshold Davis's detector could see. So from the start, the chlorine tank was not trying to catch most of the sun's neutrinos. It was only sensitive to the rare, high-energy ones, the ones produced in a particular side branch of the fusion chain involving boron-8. The boron-8 neutrinos. Those are the particles the tank was built to detect, and they make up only a small fraction of the total neutrino output of the sun. The vast, dominant stream of proton-proton neutrinos would pass through Davis's tank without leaving a single trace. This matters. File it away. We'll need it. Now, the tank itself. Davis needed a lot of dry cleaning fluid because even though there are a staggering number of chlorine atoms in any given liter of the stuff, the chance of a neutrino hitting one is so small that you need an enormous target to have any reasonable hope of catching a handful of events per week. The tank he eventually built held roughly 615 tons of tetrachloroethylene. That is approximately 380,000 litres. The size of a small swimming pool or a large one, depending on the kind of pools you're used to. Imagine, if you like, a cylindrical tank about the length of a passenger train carriage, but much, much wider. That is what Davis filled with dry cleaning fluid deep underground. The mine he chose was the Homestake gold mine in Lead, South Dakota. Lead is a small town in the Black Hills, and yes, the town is called Lead, pronounced to rhyme with feed. Named for the lead ore that was once found there, even though Homestake was primarily a gold mine, one of the deepest and most productive gold mines in the Western Hemisphere. The rock around it was ancient and dense, and that was exactly what Davis needed. He placed his tank at the 4,850-foot level. That is nearly a mile below the surface, a mile of solid Precambrian rock between the detector and the sky. Why underground? Because of cosmic rays. Out here on the surface of the Earth, we are constantly being struck by high-energy particles coming from space, protons, helium nuclei, all manner of debris from distant supernovas and other energetic events. When these cosmic rays hit the atmosphere, they produce cascades of secondary particles, including muons, which are penetrating enough to reach the ground and go some way underground. A muon passing through Davis's chlorine tank could mimic a neutrino event. It could produce argon-37 by other means and contaminate the signal he was trying so carefully to isolate. Nearly a mile of rock filters out essentially all of that background. At the 4,850-foot level, the muon flux is reduced by many orders of magnitude. The rock is a shield. The darkness is a feature. So Davis descends. The cage rattles down through the shaft, past the old workings, past the smell of rock and water and machinery, to the level where his tank sits in a carved-out cavern. This enormous silver cylinder, still and quiet, filled with something that looks like water but isn't, a liquid so ordinary that there are shops around the corner from you that use it to clean people's coats, and in that tank he waits for the sun. Or rather, he waits for the argon. Here is the remarkable thing about argon-37. It is radioactive. It decays by a process called electron capture, with a half-life of about 35 days. Which means that if you produce some argon-37 atoms inside the tank by neutrino capture and you come back a few weeks later, about half of them will have decayed. They will have converted back, in a sense, each one giving off a characteristic small burst of energy in the process of decay. And that decay signature, that tiny energy release, is what Davis's counters were designed to detect. Every few weeks, Davis and his team would run helium gas through the tank. Helium, an inert gas that does not interact with the chlorine solvent, would sweep through the liquid and carry with it any dissolved gases, including the argon, including the argon-37. The helium carried the argon out of the tank and into a processing system that isolated the argon from everything else, concentrated it, and eventually fed it into a tiny proportional counter, a small, sensitive device that could detect the radioactive decays of individual atoms. The counters themselves were remarkable objects, not much bigger than a finger, filled with the recovered argon. And over the following weeks, the counters would sit and listen, and every time an argon-37 atom decayed inside them, the counter would register a pulse. Each pulse was an atom. Each atom was tracing back through the chain, a single neutrino from the center of the sun, 8 minutes away, that had passed through everything and happened, on its way through, to brush against one particular nucleus and leave a quiet mark. Let that scale settle for a moment. The tank contained something on the order of 10 to the power of 30 chlorine atoms, that is a 10 followed by 30 zeros, a number so large that ordinary language barely touches it. Out of that staggering ocean of chlorine nuclei, Davis was expecting to produce, at the rate Bahcall's model predicted, something like one argon-37 atom every day or two, a few dozen atoms per experimental run. A handful. Not a bucketful, not a cup, not a teaspoon, a handful of individual atoms, plucked from a swimming pool of dry cleaning fluid, identified by their radioactive whisper and counted one by one. It is, when you think about it slowly, one of the most delicate measurements in the history of science. Not because the equipment was fragile, it was, in fact, rather robust. For a physics experiment, but because the signal was so breathtakingly small that the difference between the real signal and zero was almost a matter of philosophical argument. Davis had to prove that his extraction technique actually worked. Before anyone would believe a result from this experiment, especially a result that came in lower than expected, he had to demonstrate that when there were argon atoms in the tank, he could find them. So he spiked the tank. He deliberately introduced a known number of argon atoms, not argon-37, but other isotopes of argon, used as test cases, into the liquid, and ran his extraction process and counted what came out. And he showed that he could recover them. Not all of them, but a known, consistent fraction of them, enough to calibrate the efficiency of the process with confidence. He could show, in other words, that if the argon was there, he would find it. The blank result would not be an artifact of his extraction failing. If the argon wasn't there, it was because the neutrinos weren't producing it. This took years. Davis was careful in a way that suggested he understood from the beginning that what he was doing would eventually be controversial, that a result from this experiment would need to be bulletproof, because if it came back strange, people would look for every possible flaw in the method before they would look for a flaw in the physics. He was right about that. He was more right about that than he may have known. The first results came in 1968. Davis and his colleagues published what the tank had found, and the number was startling. John Bahcall's standard solar model, the detailed, carefully constructed theoretical portrait of the Sun's interior, which predicted how many boron-8 neutrinos should be arriving at the Earth, said that Davis should be seeing somewhere around 7 to 8 solar neutrino units. A solar neutrino unit, abbreviated to SNU, is a measure of the capture rate, specifically 10 to the minus 36 captures per target atom per second. It is an extremely small number, which is why they invented a special unit for it, so that people could say 7 SNU instead of saying the full decimal. Bahcall's prediction, roughly 7 to 8 SNU. That was what the model said the chlorine tank should be registering. Davis measured approximately 2.5 SNU. Roughly 1/3 of the prediction. 2/3 of the expected neutrinos were not showing up. There is a moment in science, and if you follow this subject at all, you will recognize it immediately, when a measurement comes in wrong in a way that is too consistent to be noise, but too strange to be right. The measurement says one thing, the theory says another, and the gap is large enough that somebody has to be wrong. Either the theory is wrong, or the measurement is wrong, or something that everybody thought they understood is quietly, stubbornly misbehaving in the dark. Davis had his result, 2/3 missing. And the question that would haunt physics for the next 30 years was simply this: whose fault was it? The field's instinct, almost universally, was that the fault lay somewhere close to hand, perhaps in the detector itself, perhaps in the method of extraction. Maybe some of the argon was being lost before it could be counted, and the real capture rate was higher than the measured one. Or perhaps in Bahcall's model of the sun, perhaps the solar core was not quite as hot as the model assumed. Perhaps the density profile was slightly different. Perhaps some property of the solar interior that the theory treated as known was, in fact, not known well enough. These were the comfortable explanations. They were the kind of explanations that left the fundamental physics intact. The less comfortable explanation, the one that would turn out to be correct, was that there was something wrong with the neutrino itself. That the particle, somewhere between the center of the sun and the tank in the mine, was doing something that nobody had accounted for. That the theory of what the neutrino was and how it behaved was missing something important. But that explanation was, at least in the first years, almost nobody's first instinct. Because if the neutrino was misbehaving, then the standard model of particle physics, the theory that described all the particles and all the forces in the universe, the most precisely tested and most successful theory in the history of science, would be incomplete. And the standard model said, clearly and simply, that neutrinos had no mass, that they were massless, like photons. And a massless particle, it turns out, cannot do what the neutrino would eventually be found to do. But we are still in 1968 now, or the years just after, and the measurement is sitting there, reproduced year after year, each run of the experiment confirming the same stubborn, unwelcome fraction. Let's linger with Davis for a while longer, because the experiment itself deserves more than a passing glance. There is something almost meditative about the way it ran, the slow, patient rhythm of weeks and months and years underground in the dark. Every few weeks, the team would carry out what they called a purge. The helium would flow through the tank, carefully and completely, sweeping through the liquid and displacing any dissolved gases. This had to be done thoroughly. The argon atoms had to be carried out of the tank completely and reliably, or the count would be too low for the wrong reason. The swept gas would pass through a system of traps that condensed the argon out of the helium stream. The argon was then purified further, separated from any nitrogen or other contaminants that might interfere with the counting, and eventually placed into the tiny proportional counters. And then came the waiting. The counters would sit in a lead shield, lead again, always lead, the dense metal that stops the background radiation from the rock from adding false counts to the signal. And over the following weeks, each tiny pulse would be recorded. Each time an argon-37 atom decayed inside the counter, a small voltage spike would appear. The team would analyze the pulses, check their shape to make sure they had the right signature for an electron capture decay, and count the ones that passed the criteria. That count, corrected for extraction efficiency and counter efficiency and the known half-life of argon-37, would become the measured capture rate. And run after run, year after year, it kept coming in at roughly the same low number, around 2.5 SNU, a third of what the model predicted. Davis himself, and this is worth saying clearly because later accounts sometimes lose this nuance, did not loudly proclaim that there was a crisis in physics. He was a scientist, and he reported what he found. He worked carefully to eliminate systematic errors. He improved the experiment over time. He was, by the account of those who knew him, a man of genuine equanimity, not given to drama. He had a result. He trusted his result because he had checked it every way he knew how, and he published it year after year while the physics community argued about whose fault it was. John Bahcall, meanwhile, was in a different kind of difficult position. He was the theorist whose model was being held up by many of his colleagues as the most likely source of the error. And so he did what a good theorist does when their model is challenged. He looked harder at the model. He examined every assumption, every input, every approximation. He revised the standard solar model again and again, incorporating better measurements of nuclear reaction rates, better opacities, better treatments of the solar composition. And each time he revised it, the prediction for the neutrino flux came back in roughly the same place. The model was robust. The number was real. The Institute for Advanced Study in Princeton is a quiet, beautiful place, a campus of trees and walking paths and brick buildings set back from the town, where some of the most brilliant scientists and mathematicians in the world have gone to think without the pressure of teaching. Einstein spent his last decades there. Bahcall spent much of his career there. And for 30 years he worked on the problem of the sun's neutrinos from those offices, defending a theory that the experimental results seemed to contradict, and being told, often by well-meaning colleagues, that the solar interior was simply not as well understood as he thought. That was the most common critique, that Bahcall's model of the sun was wrong. Not dramatically wrong. Nobody was suggesting that the sun was fundamentally misunderstood, but wrong in the details. Maybe the core temperature was a little lower than assumed. Maybe the heavy element abundance in the center of the sun was slightly different. Maybe the convection zone reached deeper than believed and had mixed the solar interior in ways that would change the boron-8 production rate. Any of these small adjustments, if real, could bring the predicted neutrino flux down toward what Davis was measuring. And since the sun is, after all, a very complicated ball of plasma that no human being can ever directly observe in its interior, at least not with light, it was entirely reasonable to ask whether the model of it was correct. Bahcall kept refining, he kept publishing, and the prediction kept coming back around the same value because the inputs to the model were increasingly well constrained by other observations of the sun and by laboratory measurements of nuclear reaction rates. There were people, even in the early years, who suggested a more radical possibility. Bruno Pontecorvo, an Italian-born physicist who had worked in various places including the Soviet Union, had raised the idea of neutrino oscillation in the late 1950s and early 1960s. The idea, which we will explore in much more detail later, is that neutrinos might not stay the same kind of neutrino throughout their journey. They might change. They might start as one flavour and arrive as another. And if they did, if some of the electron neutrinos born in the sun's core arrived at the Earth as something else, then Davis's chlorine detector, which could only see electron neutrinos, would measure less than the total. The missing fraction would not be missing at all. It would simply have changed into something the tank was built not to detect. This idea was discussed. It was not dismissed. But it was also not the leading hypothesis, because accepting it required accepting that neutrinos had mass, and the standard model said they didn't, and there was no other experimental evidence in the 1960s or 1970s to suggest that the standard model was wrong in this particular way. The field was not inclined to modify its most successful theory on the basis of one strange measurement from a tank of dry cleaning fluid. not without more evidence. And so the solar neutrino problem, which is what it came to be called, settled into a kind of uneasy limbo. Davis had a result, Bahcall had a prediction. The two disagreed by a factor of 3. And the field waited, and argued, and published, and waited some more, and did not resolve the question. 30 years is a long time to wait. It is a career. It is, in fact, several careers. The graduate students who started working on this problem in the early 1970s had retired by the time the answer came. The physicists who set the initial theoretical framework were, some of them, gone by the resolution. Ray Davis himself was getting older, in the mine in South Dakota, year after year, repeating a measurement that nobody could explain and nobody was entirely sure what to do with. The Homestake experiment ran for almost 3 decades. The tank sat at the 4,850-foot level, quiet in the dark, with the enormous weight of the Black Hills above it and the faint, constant stream of solar neutrinos passing through it every second. 65 billion of them through every square centimetre every second, almost all of them leaving without a trace, and just a handful. Just a few per day, stopping long enough to convert a chlorine nucleus into argon. A handful of atoms per week. That was the signal. That was 30 years of work. There is something in that image, the scale of it, the quietness of it, that seems right for this time of night. The mine, dark and still. The tank, patient. The neutrinos arriving from the sun, passing through everything. Most of them uncounted and uncountable, and just a few leaving that quiet atomic signature. Davis coming back every few weeks with his helium purge and his tiny counters, recovering the atoms and listening for their decay, writing down the number and finding it, always, about 1/3 of what the model predicted. 2/3 missing. Every run. Every year. The same number, give or take the statistical uncertainty of counting a few dozen atoms. And the question hanging over it all, unanswered, was whether 2/3 of the sun's neutrinos were genuinely disappearing somewhere between the core and the mine, which would be extraordinary. Or whether the answer was somewhere more mundane. Whether Davis had miscounted. Whether Bahcall had miscalculated. Whether the sun was, in the end, simply a little different from the model. Those were the 3 options on the table. And for 30 years, most of the field quietly preferred the second or the third. The first was too strange. The first required the particle to be doing something the theory said it could not do. And theories that have been tested as carefully as the standard model do not give up their ground easily, or quickly, or without very compelling evidence from multiple independent directions. The evidence was coming. But slowly. And not yet. For now, deep in the mine, the argon atoms decay one by one inside their tiny counters. Davis records the number. The sun keeps burning. And somewhere in the gap between the prediction and the measurement, in that gulf of 2/3, stubborn and silent, week after week, year after year, the first faint crack in the most successful theory in the history of science is already there, waiting patiently to be found. Just the mine, and the dark, and the quiet arithmetic of a few dozen atoms. And if you're still awake, that's all right. There's more to the story. There always is. But let it settle for now. Let the image of the tank and the darkness and the helium sweeping through the liquid sit with you a while. The 30 years of patience. The 2 men, Davis underground, Bahcall at his desk in Princeton, both convinced of their own measurements and their own models, and both, as it would eventually turn out, entirely correct. And the thing that was wrong between them, the thing that made the numbers disagree for 3 decades, was not the tank, and not the model, and not the sun. But that is a story for a little later, when we've had a chance to rest with the question. No hurry. The mine will keep. The answer will keep. Close your eyes if you'd like, and let the darkness of the Homestake level settle around you. Cool rock, quiet machinery, the faint drip of groundwater in the tunnel, and the invisible stream of the sun's neutrinos passing straight through everything. 8 minutes out of the core, as they always have and always will, indifferent to the argument being conducted in their name. So let's stay with it a little longer. Because the story doesn't pause when Davis records his number and climbs back out of the mine. The story, in a way, is only just beginning. What Davis has in his notebook is a measurement, and a measurement in physics is only as powerful as the explanation that eventually catches up to it. For 30 years, the explanation would refuse to come. And that is, in its own quiet way, one of the more remarkable chapters in the history of science, not a story of discovery exactly, but a story of patience, of a field confronted with an anomaly it couldn't resolve, and choosing, almost unanimously, to look elsewhere. The results began appearing in 1968. Davis published his first findings, and the number was stubborn and clear. Roughly 2.5 solar neutrino units, that peculiar measure, 10 to the minus 36 captures per target atom per second, invented largely to describe precisely this kind of rare and ghostly interaction. 2.5. Against John Bahcall's prediction, worked out from first principles and the standard solar model and everything that physics and astrophysics knew about how the sun burned, of something closer to 7 or 8. Not a little short. Not within rounding error. 1/3. 2/3 missing, and here is where the story becomes something more than a technical puzzle. Here is where it becomes human. When a physicist gets a result that disagrees with a prediction, there is a small, familiar triage that has to happen. First, is the experiment broken? Second, is the theory broken? And only then, distantly in the background, is the physics itself different from what we thought. The third option is the one that rewrites textbooks. The first two are almost always the answer. Almost always. And so the field, quite reasonably, began there. With the experiment. With the tank in the mine. Was Davis's extraction working? Had he correctly accounted for cosmic ray contamination, for stray particles that might mimic the argon-37 signal? Were the counters, those tiny proportional tubes measuring single radioactive decays, performing accurately? Was the spiking procedure, adding known quantities of argon to the tank to verify the chemistry, truly confirming what he thought it was confirming? These are not unreasonable questions. They are exactly the right questions. And Davis, for his part, had already asked all of them, repeatedly, before he published anything. The spike tests had worked. The extraction chemistry was verified. The counters were calibrated. He had done, by every accounting, an extraordinary piece of experimental science, under conditions that most laboratories would have found frankly implausible. A few dozen atoms from a swimming pool of liquid deep underground. And he was confident in the number. But confidence in science is not the same as proof. And the gap between 2.5 and 7 was wide enough that confidence by itself was not going to satisfy anyone. So the first decade or so after 1968 was spent in a kind of sustained, respectful, professionally polite interrogation of Ray Davis's tank. People looked for systematic errors. People proposed alternative explanations for where a few extra argon atoms might be coming from, or where some might be lost. People questioned the threshold, questioned the efficiency, questioned the counting statistics. Davis answered, methodically, patiently, and the tank held up. And then the attention began to drift, slowly but unmistakably, toward the second option. Maybe the sun is wrong. Not wrong in some catastrophic sense. Not wrong in a way that should worry you about tomorrow morning's sunrise, but wrong in the specific technical sense that John Bahcall's standard solar model, his careful, painstaking calculation of the temperatures and densities and nuclear reaction rates in the solar core, might have gotten some detail incorrect. The sun, after all, is not a machine anyone has inspected from the inside. It is a calculation. A very good calculation, built on decades of nuclear physics and stellar physics and careful measurement of the solar luminosity and composition and age. But still a calculation. And calculations have assumptions. And assumptions can be wrong. The most attractive version of this idea was temperature. The boron-8 neutrinos, the ones Homestake was sensitive to because of its 0.814 MeV energy threshold, are extraordinarily sensitive to temperature in the solar core. The rate at which boron-8 is produced goes something like the 18th power of the temperature. 18. That means a relatively small drop in core temperature, a few percent, would produce a very large drop in boron-8 neutrinos. If the core of the Sun was slightly cooler than Bahcall's model said, you might naturally expect exactly the kind of deficit Davis was seeing. This is a clean, testable hypothesis. It does not require any new physics. It does not require rethinking the standard model of particle physics. It requires only that our model of the Sun's interior be imprecise in a modest and explicable way. It was a comfortable idea, and for a while it was widely held. John Bahcall did not think the Sun was cooler than his model said. This is where the human element of the story becomes harder to summarize neatly, because Bahcall occupied a peculiar position. He was, simultaneously, the man whose prediction the experiment had failed to confirm, and the man most committed to defending the prediction. He spent years, and then a decade, and then 2 decades, refining the standard solar model, looking for errors in his own work, updating the nuclear reaction rates as laboratory measurements improved, adjusting the opacity estimates, incorporating new data on the Sun's composition. Every time the model was updated, the prediction for the boron-8 neutrino flux changed a little, and every time it changed, the discrepancy with Homestake remained. It didn't close. If anything, as the years went on and the calculations became more precise, the model grew more confident in its own prediction, and the prediction remained stubbornly inconsistent with what Davis was measuring. But the field, or a substantial part of it, continued to treat this as a problem with either the experiment or the model rather than with the physics. Bahcall was told, in various ways and with various degrees of kindness, that his Sun was simply misunderstood, that the solar core was a more complicated place than his model allowed, that astrophysics, unlike particle physics, dealt with objects you could not hold in your hand or put in an accelerator, and that uncertainty was simply part of the territory. He kept calculating. Let's let that sit for a moment. The picture of it. John Bahcall, at his desk at the Institute for Advanced Study in Princeton, the same rarefied institution where Einstein spent his final decades, where Oppenheimer directed the early post-war years, working through the numbers again and again and again. Not because the field was demanding it, sometimes in spite of the field's indifference, because he believed the model was right, and because he believed that an unexplained measurement was a challenge worth taking seriously rather than a nuisance to be explained away. There's something almost old-fashioned about it, in the best sense, something that belongs to the same category of scientific stubbornness as Wegener insisting the continents once fit together while geologists laughed, or Semmelweis washing his hands when nobody else would. Conviction, held quietly, in the face of extended professional skepticism. And the anomaly had a name, by now. It had been called the solar neutrino problem since the early 1970s, and the name itself says something interesting. It was a problem with the solar neutrinos, not, as it would eventually turn out, a problem with the neutrinos as such. The framing built the assumption in solar, the sun's fault, or Davis's count. The neutrino itself as a physical entity was not, for most of this period, the prime suspect. There were voices that disagreed. Bruno Pontecorvo, a Soviet-Italian physicist who had thought about neutrinos as deeply as anyone alive, had speculated as early as the 1960s that neutrinos might oscillate between types, that the particle born as one flavour might transform into another in flight, the way a gyroscope slowly precesses if something is pushing on it. If that were true, a detector sensitive to only one flavour might simply be blind to the neutrinos that had changed. Not missing. Changed, but Pontecorvo's idea required neutrinos to have mass, a small but non-zero mass, and the standard model said they had none. So the oscillation idea floated at the margins of the conversation, taken seriously by some and quietly filed under interesting speculation by many others. The mainstream read kept coming back to the sun, or the tank, and then the escape hatches started closing. The first one to close was slow and quiet and arrived not from underground but from above. From the surface of the sun itself. Here is something worth knowing, if you don't already, and it's the kind of thing that makes you look at an ordinary sunrise differently. The sun rings. Not like a bell, exactly, or not like any bell you'd recognize, but like a bell in the way that matters mathematically, in standing waves. Its interior drives pressure oscillations that propagate through the solar body and produce subtle, periodic motions at the surface. The surface of the sun rises and falls in certain regions by tiny amounts at characteristic frequencies, and those oscillations carry information, the way the pitch of a drum carries information about the drum's size and tension. If you listen carefully enough to the way the sun's surface moves, you can infer what its interior looks like. This is Helioseismology, the study of the sun's vibrations as a way of seeing inside it, and through the 1980s and into the 1990s, Helioseismology became increasingly precise. Networks of ground-based telescopes, including the GONG network, the Global Oscillation Network Group, a ring of 6 observing stations spaced around the Earth to keep the sun in view at all times, measured the solar surface velocities in extraordinary detail. And the SOHO spacecraft, launched in 1995 and stationed between the Earth and the Sun at the first Lagrange point, contributed its own exquisitely precise measurements from a vantage point above the blurring effects of the atmosphere. The measurements were compared with what Bahcall's standard solar model predicted. They matched, not approximately. Not within a comfortable uncertainty range that left room for the core to be a few % cooler. They matched to a fraction of a percent. The internal sound speed profile of the sun, the way seismic waves travel through its layers at different depths, traced out a curve that corresponded, almost exactly, to the temperature and density structure that Bahcall's model had been predicting for years. The solar core was not cooler than Bahcall said. It was not differently structured. It was, to the degree that Helioseismology could resolve it, essentially as he had described. The sun is wrong explanation had just had its legs taken out. This was a significant moment, and it deserves to be felt as one, even from a distance of several decades. For years, the comfortable assumption had been that the solar model was the weak link, that astrophysics was imprecise enough that a 30% discrepancy in a predicted neutrino flux was within the territory of model uncertainty. Helioseismology closed that argument. The sun was not wrong. The sun was Bahcall's sun to a precision that no one could now seriously contest, which left the experiment, or the physics, and the experiment was about to get some unexpected company. Because Davis's chlorine detector, for all its extraordinary achievement, had one significant limitation built into its design: the energy threshold. The reaction that turned chlorine-37 into argon-37 required an incoming electron neutrino with at least 0.814 million electron volts of energy. That was high enough to exclude the vast majority of solar neutrinos, the ones produced by the basic proton-proton chain, the central fusion reaction that powers the sun, which come out with much lower energies. Homestake was only sensitive to the rarer, high-energy neutrinos from secondary reactions, particularly the boron-8 branch. So it was, in a real sense, a narrow window onto a specialized slice of the total solar flux. One way to attack the anomaly, then, was to argue about threshold effects. If the boron-8 neutrino production specifically was suppressed by a cooler core, by some detail of the nuclear reaction rates, you might see a deficit in the chlorine detector that didn't reflect what was happening with the dominant low-energy pp neutrinos. Homestake, by itself, couldn't check. It simply couldn't see the pp neutrinos. But gallium could. Gallium-71. The isotope of gallium with 71 nucleons, which reacts with an electron neutrino at a threshold of only 0.233 million electron volts, well below the energy of the proton-proton neutrinos. A gallium detector would, in principle, be sensitive to the whole broad solar flux, not just the rare high-energy branch. If you ran a gallium experiment and saw the full predicted number, you could argue that Homestake's deficit was a high-energy artifact. If you ran a gallium experiment and still saw a deficit, you had sealed off another escape route. 2 gallium experiments ran, and they found a deficit. Gallix, the gallium experiment, was located in the Gran Sasso underground laboratory in Italy, inside the mountain of the same name in the Apennines, beneath more than a kilometre of rock. It ran through the 1990s, succeeded by the Gallium Neutrino Observatory, which continued the measurement with refined techniques. Thousands of miles away, in the Baksan Valley in Russia, SAGE, the Soviet-American gallium experiment, was doing the same thing, independently, in the Baksan Underground Scintillator Telescope facility. Both experiments saw fewer neutrinos than predicted. Not the same fraction as Homestake. Necessarily, the energy dependencies were different, and the predicted flux for pp neutrinos is both large and more robustly calculated, but a deficit nonetheless. The total was low. The gallium experiments were sensitive to the pp neutrinos that Homestake couldn't touch, and they found that those too were arriving in reduced numbers. So it wasn't a threshold artifact. It wasn't something peculiar about boron-8. The problem was the solar neutrino flux as a whole, at every energy that anyone had managed to probe. Close the second escape hatch. Settle back for a moment, because this is where the situation becomes, if you take a step back and look at it with fresh eyes, genuinely strange. You have an experiment that has been running for decades, underground in a gold mine in South Dakota. You have a theoretical model that has been refined for decades at one of the great institutions of academic physics. Helioseismology has now confirmed the model's internal structure to a fraction of a percent. Gallium experiments running independently in Italy and Russia have confirmed that the deficit is not an artifact of the energy window. Everything that could have been wrong within the conventional assumptions of solar physics and detector calibration has been checked and ruled out. And yet the number keeps coming back low, 2.5 against 7 or 8. Week after week, a few dozen argon atoms when the model says there should be more than 3 times as many. Something somewhere is not right. And the two most comfortable somethings, the sun and the tank, have both now been cleared. What's left is the neutrino itself. But let's not jump ahead, because the third piece of this particular closing, the third confirmation that something genuinely strange was happening to the neutrinos in transit, came from Japan. From a place even more deeply buried than Homestake, and from a detector of a radically different kind. The Kamioka mine sits in the mountains of the Gifu prefecture in Japan, a zinc mine worked out over generations and now hosting a different kind of industry entirely. In the 1980s, a detector called Kamiokande was built there. Kamioka nucleon decay experiment, though the neutrino results would eventually overshadow its original purpose. The mine went deep. The detector sat far from the surface, shielded by enough rock to muffle most of the cosmic ray background that would otherwise swamp the signals it was trying to catch. And the detector was fundamentally different from Davis's tank. Not chemistry, not atoms. Kamiokande was a water Cherenkov detector, a large tank of very pure water surrounded by photomultiplier tubes, sensitive light detectors. Thousands of them, watching the interior of the tank in every direction. When a neutrino occasionally collides with an electron in the water and sends it flying, that electron, if it is travelling fast enough, emits a faint cone of blue light, Cherenkov radiation, named for Pavel Cherenkov, who received a Nobel for its description in 1958. The photomultiplier tubes around the tank pick up this light, and from the pattern of the signal, its direction, its timing, its brightness, the detector can reconstruct the direction the neutrino came from and estimate its energy. This is the key difference. Davis's chlorine tank told you how many events occurred, but not where the neutrinos came from, and not when each individual event happened. Kamiokande could point back at the source. Masatoshi Koshiba led the experiment at Kamioka, and what Kamiokande showed, and this was important because it was precisely the kind of check that skeptics had wanted, was that the neutrinos were genuinely coming from the direction of the sun, not from the surrounding rock, not from cosmic ray contamination that happened to produce a similar signal. When a solar neutrino interacted in the tank, the recoiling electron flew roughly in the direction the neutrino had been travelling, which was, to within the angular resolution of the detector, the direction of the sun. The neutrinos were real, they were solar, and they were fewer than predicted. Kamiokande confirmed the deficit independently, with a different detector technology and a different detection reaction, in a different country, under a different mountain. And it confirmed it directionally. It pointed at the sun and said, yes, this is the right source, and there are still too few. That mattered enormously for the credibility of the whole body of evidence. It meant you could no longer argue that Davis's experiment had some unique systematic error producing a spurious deficit. Two independent experiments, using completely different methods, both found too few solar neutrinos. The anomaly was real. And then, in 1987, Kamiokande did something nobody had planned for. On the 23rd of February 1987, a massive star in the Large Magellanic Cloud, a small companion galaxy to our own Milky Way, roughly 168,000 light-years away, completed its collapse and exploded. Supernova 1987A. The first naked-eye supernova visible from Earth since 1604, it became one of the most studied astrophysical events in modern history, and when a star collapses, it releases an enormous fraction of its gravitational energy, the equivalent of something like 10 to the power of 46 joules, almost entirely as neutrinos. A supernova is, in the first seconds of its collapse, one of the most intense sources of neutrinos in the observable universe. It emits, in those seconds, more neutrinos than the Sun will emit in 10 billion years. Kamiokande caught them. Not just one or two. 11 neutrino events arrived in the Kamioka detector in a burst spanning about 13 seconds, consistent with the expected timing of a stellar collapse. At essentially the same moment, give or take the different depths and configurations of the respective detectors, a detector called the Irvine, Michigan Brookhaven experiment in a salt mine in Ohio caught 8 events, and a detector in the Baksan Valley in Russia caught 5. 11, 8, 5, 24 neutrinos total from a source 168,000 light-years away. This was the first time in history that neutrinos had been detected from an astronomical source other than our own Sun. It confirmed, in a single dramatic burst, that core collapse supernovae are driven by neutrino emission in exactly the way that theory predicted. It confirmed that the neutrinos were travelling at approximately the speed of light across cosmological distances. And it confirmed that Kamiokande was a functioning, reliable, astrophysically sensitive instrument, not a detector manufacturing phantom signals, but a machine genuinely watching the sky through a kilometre of Japanese mountain. The 1987A detection elevated the entire field. It demonstrated that neutrino astronomy, actually reading the cosmos through its neutrino emission, not just through light, was not a theoretical fantasy, but a practical reality. The particles were there, the detectors could catch them, the signals were real, and the solar deficit was still real too. Unchanged by 1987A, unchanged by Helioseismology, unchanged by the Gallium results from Italy and Russia. A third of what Bahcall predicted, week after week, year after year, with increasing numbers of independent confirmations and decreasing numbers of places to hide the explanation. Koshiba would later receive the Nobel Prize in Physics in 2002, together with Ray Davis, for his role in building and running these underground neutrino observatories. But that is still ahead in the story. In the late 1980s and early 1990s, what Kamiokande's results meant was simpler and more immediate. The anomaly was confirmed. The experiment was working. The neutrinos from the Sun were genuinely depleted. Bahcall was right about the Sun, Davis was right about the count, and there was now a list of experiments in 4 different countries using 3 different detection techniques, all saying the same thing. Too few. Too few. Too few. There's a particular kind of intellectual discomfort that comes with this situation, and it's worth sitting with for a moment, because it's one of the less comfortable truths about how science actually works. A single anomaly is easy to dismiss. One man in one mine, with 1 tank of dry cleaning fluid, says the number is low. That's one data point. You can question it. You can call it a systematic error. You can chalk it up to an idiosyncrasy of the detector, or the extraction chemistry, or the calibration. But by the late 1980s and into the 1990s, the solar neutrino problem had been confirmed by chlorine chemistry in South Dakota, by water Cherenkov light in Japan, by gallium chemistry in Italy, by gallium chemistry in Russia. It had been established over a period of more than 20 years by multiple research groups working independently, with overlapping and cross-checking methodologies. The error bars had been examined, re-examined, and examined again. The systematic uncertainties had been itemized and accounted for. And it was still a third. At some point, and this is the difficult thing to pin down historically because it happens gradually and not all at once, the field's center of gravity began to shift. The comfortable narrative, Davis miscounted, or Bahcall's sun is wrong, was becoming harder to sustain. Not impossible. Not everyone had abandoned it, but harder. The evidence was accumulating on the side of the anomaly being real and unexplained. But unexplained by what? If it wasn't the experiment, and it wasn't the model of the sun, what was it? The answer that was sitting in the background, the one that Pontecorvo had sketched the outlines of decades earlier, and that a handful of theorists had continued developing through the long quiet years of the solar neutrino problem, required taking seriously something the Standard Model explicitly forbade. And we'll come to that. We will absolutely come to that. But the path there runs through one more detector, a detector that would, when its data finally came in, resolve the question not by reducing the uncertainty, but by asking it from two directions at once. For now, though, for this part of the night, let the evidence accumulate at its own pace. Let the picture build. 4 experiments, 20+ years. Helioseismology matching Bahcall's sun to a fraction of a percent. Gallium ruling out the threshold argument. Kamiokande pointing back at the actual sun and catching supernova 1987A along the way, proving its own instruments were real and its own signals were trustworthy. The escape hatches are closing, one by one. And in Bahcall's office at the Institute for Advanced Study in Princeton, the calculation keeps getting refined. Every year or two, a new version of the standard solar model. Every new version checked against fresh helioseismological data. Every check confirming the same interior structure. Every confirmation making the case a little stronger that the solar model is not where the problem lives. He was not, by the accounts of people who knew him, a man who wore his frustration publicly. He was methodical. He was precise. He was someone who had spent his career asking the sun a specific question and keeping meticulous track of the answer, and when the answer didn't match, he updated his instruments and asked again rather than deciding the question must have been wrong. There is a kind of scientific faith in that, not faith in a religious sense, but faith in the integrity of a measurement and in the possibility that the universe will eventually tell you something true if you ask carefully enough and listen patiently enough. He would have to wait a long time. And the neutrinos, the ones already passing through the floor beneath you right now, through the mattress or the cushion or whatever, is between you and the ground, 65 billion of them for every square centimetre of your body every second, most of them having left the solar core about 8 minutes ago. They don't wait. They don't stop. They pass through the Earth as if it weren't there, and some small fraction of them interact with the atoms of our detectors, and we record those interactions, and we count them, and we find they are fewer than we expected. They have always been fewer than expected. And the question of why, the question that Davis first posed in 1968, with a number written in a notebook at the bottom of a gold mine in South Dakota, that question is still, at this point in the story, open, but not for much longer. Because there is another detector being built. Not in South Dakota. Not in Japan. farther north, underground in a different kind of mine, using a material that no solar neutrino experiment has tried before. And this one is going to be able to ask the question in a way that no previous detector could, from two directions simultaneously, in such a way that the answer cannot hide. It's in Ontario, Canada. It's being lowered, piece by careful piece, into a nickel mine. And it's filled with something that looks like water, but is not quite water. 1,000 tons of it, heavy and still and cold, in the dark, 2 kilometres below the Canadian Shield. And somewhere in the logic of how that detector works, in the distinction between two kinds of particle interaction it was designed to observe, the 30-year anomaly is about to become something else entirely. Not a problem, in the end, a discovery. But that is the next part of the journey. And there's no hurry. The detector will keep. The result will keep. For now, let the list of closed escape hatches settle around you like the walls of the mine. The sun is right. The tank is right. The gallium experiments are right. Kamiokande is right. All of them pointing at the same stubborn gap. All of them confirming, in their different ways, that the neutrinos arriving from the sun are fewer in number, by a third, roughly, depending on the detector and the energy range, than the most precise model of our star says they should be. And somewhere in that gap, patient and invisible, the answer is already there. It was always there. It was arriving in the tank the whole time, wearing a face the chlorine couldn't see. The Sudbury Neutrino Observatory took years to build. It had to. You cannot rush a project like this, not because of bureaucracy or funding delays, though there was plenty of both, but because the physics itself demanded patience at every step. The heavy water had to be borrowed, on loan from Atomic Energy of Canada, because 1,000 tons of the substance costs roughly $300 million, and nobody was simply going to hand that over without a plan for getting it back. The mine shaft had to be prepared. The acrylic sphere that would hold the water, 12 meters across, transparent and flawless, assembled by hand from panels in the dark, had to be lowered in sections and joined underground with a precision that allowed no room for error, because a leak 2 kilometres beneath the Canadian Shield is not the kind of problem you fix with a wrench and a bucket. Arthur B. McDonald led the collaboration. He was a Canadian physicist, and the choice of Canada mattered in a practical sense. The Creighton nickel mine near Sudbury, Ontario, was already deep, already operational, already dug. The 2 kilometres of rock overhead would serve the same purpose as the 4,850 feet of South Dakota that sheltered Ray Davis's tank. Silence. Cosmic silence. The kind of quiet you can only find underground, where the ordinary background hum of the universe. The cosmic rays that rain down on every surface every second cannot penetrate. But snow was not simply another homestake. It was not simply another underground tank waiting for a neutrino to wander through. The thing that made it different, the thing that made it the answer to the question the field had been unable to answer for 30 years, was the material inside it and the two completely different reactions that material could support. Heavy water. You have heard of ordinary water, of course, 2 hydrogen atoms and 1 oxygen. Ho, the thing in your glass and your bloodstream and the clouds outside. Heavy water is the same molecule, except that the hydrogen atoms are replaced by deuterium, a heavier form of hydrogen whose nucleus contains not just 1 proton, but 1 proton and 1 neutron. The chemical symbol is DO. It looks identical to ordinary water. It tastes the same. If you drank it, you would not immediately notice any difference. though drinking large quantities of it would eventually be harmful, which is not a concern here. What matters is the deuterium nucleus, the deuteron, and what a neutrino can do to it. There are two things a neutrino can do to a deuteron, and these two things respond to the neutrino world in completely different ways. The first reaction is what physicists call a charged current interaction, an electron neutrino, specifically an electron neutrino, not a muon neutrino or a tau neutrino, arrives and strikes the deuteron and converts one of its neutrons into a proton. The deuteron breaks apart. You get two protons and a fast-moving electron, and that electron travels through the heavy water fast enough to produce a faint cone of light, Cherenkov radiation, a kind of optical shock wave, the same blue glow you sometimes see in photographs of nuclear reactors submerged in water. The detectors lining the sphere, nearly 10,000 photomultiplier tubes, each one a glass eye trained on the heavy water, can see that light and record it. And critically, this reaction only works for electron neutrinos. A muon neutrino, arriving with the same energy, with the same momentum, streaming in from exactly the same direction, passes straight through the deuteron without triggering this reaction at all. The charged current measurement is flavor-specific. It sees one type and only one type. The second reaction is a neutral current interaction. A neutrino, any neutrino, of any flavor, arrives and strikes the deuteron and breaks it apart without converting anything. You get a free proton, a free neutron, and the neutrino continues on its way, barely changed. The free neutron eventually gets captured by another nucleus and releases a gamma ray, which the photomultiplier tubes also detect. This reaction is completely flavor-blind. It does not know or care whether the arriving particle is an electron neutrino or a muon neutrino or a tau neutrino. It sees them all equally. It counts the total, regardless of flavor. Do you see what this gives you? If you can run both reactions simultaneously in the same detector using the same 1,000 tons of heavy water, the same photomultiplier tubes, the same underground installation, then you get two numbers. One is the electron neutrino flux from the charged current reaction. The other is the total neutrino flux of all flavors combined from the neutral current reaction. And the ratio between those two numbers tells you everything. If the two numbers are the same, the neutrinos are not changing flavor. The electron neutrinos are arriving as electron neutrinos and being counted correctly, and the total and the individual tally agree. No oscillation. If the first number is smaller than the second, if the electron neutrino count is lower than the all-flavor total, then something has changed. Some of the electron neutrinos that left the Sun have arrived as something else. They started the journey as one thing and finished it as another. And the neutral current measurement, blind to flavor, caught them anyway. Snow published its results between 2001 and 2002. And the numbers were, in the language of physics, decisive. The charged current measurement gave a solar electron neutrino flux in rough agreement with what Ray Davis had been measuring in his chlorine tank since 1968. Roughly 1/3 of what John Bahcall's standard solar model had predicted. The same deficit, the same stubborn 30-year gap. But the neutral current measurement, the all-flavor total, the count that did not care what the neutrino looked like when it arrived, gave a completely different number. It gave a total flux that matched Bahcall's model almost exactly. Almost exactly. Think about what that means. Sit with it for a moment. The Sun was producing the right number of neutrinos all along. Bahcall's model of the solar core, the fusion rates, the temperatures, the proton-proton chain, all of it was right to within the measurement uncertainties of the experiment. The total arriving at the detector matched the total predicted to leave the Sun. The neutrinos were not missing. They had never been missing. What had happened? What had been happening for the entire 30 years that Ray Davis's tank kept returning its stubborn third was that roughly 2/3 of the electron neutrinos produced in the solar core were arriving at Homestake and at Snow and at every other detector on Earth, having changed their identity in flight. They had left the Sun as electron neutrinos. They arrived at the chlorine tank as muon neutrinos and tau neutrinos, and a chlorine atom cannot capture a muon neutrino. The reaction simply does not happen. The energy thresholds and the quantum numbers do not match. The chlorine was counting only the fraction that had remained as electron neutrinos for the entire journey across 93 million miles of space. It was deaf to the other 2/3. Davis's tank was not broken. Bahcall's model was not wrong. The accounting had been perfect the whole time, in a different column than anyone had thought to look. Now there is a beautiful and slightly unsettling piece of physics underneath all of this, and it is worth taking slowly, because it is the part that broke something. A neutrino, when it is created in a definite flavour state. An electron neutrino is produced in the Sun's core as part of the proton-proton fusion chain. A proton becomes a neutron, emitting a positron, and an electron neutrino as part of the vast machinery that keeps the Sun burning. That neutrino has a definite flavour at the moment of its birth. But, and here is the strangeness, a definite flavour is not a definite mass. Quantum mechanics allows particles to exist in superpositions. You may have encountered this idea in the context of Schrödinger's cat or the double-slit experiment. But neutrinos offer their own version of the same idea, and it is arguably more practically consequential. The three neutrino flavors, electron, muon, tau, are each a mixture, a quantum superposition of three different mass states. Physicists call these mass eigenstates, and they label them with numbers: mass state 1, mass state 2, mass state 3. An electron neutrino is a particular combination of all three mass states, with particular weightings that quantum mechanics specifies with extraordinary precision. Now, these three mass states have different masses. They are not the same. Even a tiny difference matters, because when the neutrino flies through space, each mass state travels at a very slightly different rate. Not a different speed exactly, since all three move extremely close to the speed of light, but a slightly different relationship between energy and momentum that means their quantum phase evolves at a slightly different rate. And because the electron neutrino is a superposition of all three, the phases of the components gradually drift apart as the neutrino travels. The mixture shifts. What started as the combination of components that defines an electron neutrino slowly, continuously rotates into a different combination. First it becomes partly a muon neutrino, then partly a tau neutrino, then back again, oscillating, cycling through flavours like a slowly turning key in a lock, over a distance that depends on the energy and the mass differences involved. This is neutrino oscillation. The particle changes identity in flight, not because anything acts on it, not because it collides with anything, but because its quantum nature is evolving as it travels. The way a tuning fork produces a note that is actually a superposition of many frequencies, each drifting in and out of phase with the others. And here is the crack in the wall, the thing that broke the standard model. A particle can only oscillate between mass states if those mass states have different masses. Not just any masses, they must differ. If all three mass states had exactly the same mass, even a mass of 0, the phases would evolve identically and the flavour would never rotate. Oscillation requires a mass difference. A mass difference requires that at least 2 of the 3 mass states have non-zero mass. The standard model of particle physics, as it was written and as it had stood since the 1970s, contained exactly massless neutrinos. Not approximately massless. Exactly. The theory had no mechanism for giving them mass. The structure of the model simply did not accommodate it. Neutrino mass was not a small correction waiting to be measured. It was, in the theory, forbidden, Snow's result, confirmed independently and cross-checked by multiple experiments. Was a direct measurement that neutrinos change flavour and therefore must have mass. This is not an inference or a statistical suggestion. It is a logical necessity built into the mathematics of quantum mechanics. Oscillation implies mass difference. Mass difference implies mass. Mass breaks the standard model. For 30 years, the field had been sitting on the first measured failure of the most precisely tested theory in the history of science, and the most common explanation was that the chemist in South Dakota had miscounted his argon atoms. Before Snow published its solar result, there had already been a powerful forewarning from the other side of the world. Super Kamiokande is in Japan, in the Kamioka mine in Gifu Prefecture. It is a cylinder of ultra-pure water 50 meters tall and 39 meters in diameter, roughly 50,000 tons of water, lined from floor to ceiling with about 11,000 photomultiplier tubes, each one watching. It succeeded the earlier Kamiokande detector that Masatoshi Koshiba had built, which had already shown that solar neutrinos were genuinely deficient, and had, in a separate triumph in 1987, caught neutrinos streaming from a supernova in the Large Magellanic Cloud, supernova 1987A, the first time neutrinos from outside our own solar system had ever been detected. That detection, by the way, arrived almost simultaneously at Kamiokande, and at a detector in Ohio, and at one in Russia, a burst of 19 neutrinos arriving within seconds of each other, and about 3 hours before the light from the explosion, because neutrinos travel through the dense stellar material almost as freely as through nothing, while light had to fight its way out. But Super Kamiokande's great contribution to the neutrino oscillation story came in 1998, and it came not from solar neutrinos at all, but from cosmic ray muon neutrinos, the atmospheric neutrinos. When cosmic rays strike the upper atmosphere, they produce a rain of secondary particles, including muon neutrinos and electron neutrinos, in a predictable ratio. Super Kamiokande could detect neutrinos coming down from directly overhead and neutrinos coming up through the Earth from below, having been produced on the opposite side of the planet and travelled through roughly 12,000 kilometres of rock and mantle to reach the detector. Those upward-going neutrinos, coming from the far side of the Earth, had been travelling for roughly 2 orders of magnitude longer than the overhead ones. And what Super Kamiokande found, announced in 1998, was that the muon neutrinos coming up from below, the ones with the longer journey, were fewer than the muon neutrinos coming from overhead. Not the electron neutrinos, the muon neutrinos. The muon neutrinos were disappearing in transit, their numbers depleted by the extra distance they had to travel, in a pattern that fit the quantum mechanical prediction for oscillation beautifully. The longer the path, the more time for the phases to drift, the more of them had rotated into tau neutrinos by the time they arrived. Takaaki Kajita led this analysis. He and his team stood up at a conference in Takayama, Japan, in June of 1998 and showed the world that atmospheric muon neutrinos were oscillating into tau neutrinos, and that this oscillation required mass. The result was clear enough and the statistics clean enough that the physics community, which had been skeptical for 3 decades, could not look away. The atmospheric result was the hammer blow. Snow's solar result, arriving in 2001 and 2002, was the knockout. And they were different enough in their details, different particle types, different energies, different detectors, different countries, that they could not both be wrong in the same convenient direction. Together, they constituted something close to proof. Camland, a different Japanese detector, added a third layer of confirmation. It was not looking at solar neutrinos or atmospheric neutrinos. It was looking at antineutrinos from the dozens of nuclear reactors scattered around Japan. Reactor antineutrinos, produced in enormous quantities by the fission of uranium and plutonium, could be detected at a distance, and their numbers counted. And what Camland found, announced in 2002 and refined in the years following, was that reactor antineutrinos also disappear in transit, at a rate and a distance dependence that perfectly matched the same oscillation parameters that the solar experiments and the atmospheric experiments had extracted. 3 different sources, 3 different detectors, 3 different countries. One set of underlying numbers describing a universe in which neutrinos have mass and the standard model is incomplete. There is something worth pausing on in the middle of all this physics, and it has to do with 2 men and the particular shape of their vindicatino. Ray Davis and John Bahcall had worked together in a real sense for decades, not as adversaries, as collaborators, each one needing the other. Davis needed Bahcall's prediction to know what his detector should see. Bahcall needed Davis's result to know whether his model was right. They were bound together by the anomaly, and they weathered the long middle years, the years when the field's default assumption was that one of them had made an error, with what those who knew them describe as a particular combination of stubbornness and good humour. Bahcall kept refining his numbers. Davis kept counting his argon atoms. Neither one blinked. In 2002, the Nobel Prize in Physics was awarded. Raymond Davis Jr. received half of it, shared with Masatoshi Koshiba, for the detection of cosmic neutrinos. Davis was 88 years old. He had begun building his experiment in the 1960s and spent the better part of 4 decades watching a deficit he could not explain and being told, with various degrees of politeness, that his tank was the problem. And now here was the Nobel Committee, the most authoritative body in physics, saying it was never the tank. He was 88. And he had been right the whole time. Koshiba, whose Kamiokande detector had independently confirmed the solar deficit and had caught those 19 neutrinos from supernova 1987A, received the other half. And Bahcall? John Bahcall, who had built the standard solar model from the ground up, who had spent 3 decades defending it against a near-universal assumption that his son must be wrong, who had watched Helioseismology vindicate his numbers and then watched snow prove that the total flux was exactly what he had calculated, John Bahcall did not receive a Nobel Prize. The committee awarded the Physics Prize in 2002 for the detection of the neutrinos themselves, and in 2015 for the discovery of oscillation. Neither category quite fit Bahcall's contribution in a way the committee apparently found compelling enough to recognize directly. He died in 2005. He was 69 years old. He died having seen his model vindicated as completely as a model can be vindicated. He knew the sun was right. He knew the standard solar model was right. He knew that the thing he had spent his career calculating was not wrong. That must have been something, in the end, even without the prize. Davis died the following year in 2006. He was 91. The 2015 Nobel Prize in Physics went to Takaaki Kajita and Arthur B. McDonald for the discovery of neutrino oscillations. The prize committee's language was precise. They had discovered that neutrinos change identity, and that this discovery shows neutrinos have mass. 13 years after Davis's prize, and 57 years after Davis first lowered his tank into a South Dakota gold mine, the full arc of the story finally had a bookend. But here is the thing about physics. The answers do not close the door. They open more of them. The fact that neutrinos have mass is now settled, demonstrated beyond any reasonable argument, confirmed by multiple independent experiments using multiple techniques across multiple decades. But how much mass? In what order? In what pattern? Those questions remain. And they are not small questions. They sit at the edge of what the field currently knows, and they are being asked right now, tonight, in laboratories and mines and ice fields that stretch from the bottom of a Canadian nickel mine to the literal bottom of the world. The three mass states have masses, but we do not yet know which one is heaviest. This is called the mass ordering, or the mass hierarchy. There are two possibilities. In the normal ordering, the first and second mass states are lighter, and the third is heavier, the same rough pattern you see with quarks and charged leptons. In the inverted ordering, the third mass state is lighter, and the first and second are heavier. Both are consistent with everything currently measured. Pinning down which one is true would tell physicists something important about the deeper structure of the theory that will eventually replace or extend the standard model. Then there is the question of the sterile neutrino. The three flavours we have talked about tonight, electron, muon, tau, interact with ordinary matter via the weak force. They are, in that sense, not invisible, but merely shy. They interact rarely, but they do interact. A sterile neutrino, if it exists, would not interact via the weak force at all. It would pass through ordinary matter without any interaction whatsoever, detectable only through its effects on oscillation. There have been hints of sterile neutrinos in anomalies from various experiments over the years, but nothing conclusive. The field is watching. And then there is perhaps the deepest question of all. What is the neutrino at its most fundamental level? There are two possibilities for a neutral particle. It can be a Dirac fermion, meaning it is genuinely distinct from its own antiparticle. There is a neutrino and a separate antineutrino, and they are different. Or it can be a Majorana fermion, meaning the particle and the antiparticle are the same thing. The neutrino is its own antiparticle. For every other particle we know about, matter and antimatter are distinct. But for a neutral particle, there is no electrical charge to distinguish them, so the question is genuinely open. The way to test this is to look for a process called neutrinoless double beta decay. Ordinary double beta decay is a rare nuclear process in which two neutrons simultaneously decay into two protons, emitting two electrons and two antineutrinos. It happens. It has been measured. But if the neutrino is its own antiparticle, there exists an even rarer process in which the two antineutrinos, being identical to neutrinos, annihilate each other internally and never appear in the final state. You get two electrons and nothing else, no neutrinos, no antineutrinos, because they cancelled each other out. Seeing that signature, finding those two lonely electrons with their characteristic energy, would tell you immediately and definitively that the neutrino is a Majorana particle. Several experiments around the world are looking for this signature right now. None have found it. But the search continues because the answer matters far beyond particle physics. If the neutrino is a Majorana particle, it opens a pathway to explaining one of the deepest puzzles in all of cosmology, why the universe is made of matter rather than antimatter. The Big Bang should have produced equal amounts of both, and they should have annihilated each other into pure energy, leaving nothing, no stars, no planets, no mines, no tanks of dry cleaning fluid, no one to wonder about any of this. And yet here we are, surrounded by matter. Something broke the symmetry. Some process in the very early universe favoured matter over antimatter by a tiny, crucial amount. The neutrino, if it is a Majorana particle, might have been the agent of that asymmetry. This pathway is called leptogenesis, and it connects a peculiar feature of a particle counted in argon atoms in a South Dakota mine to the question of why anything exists at all. The experiments looking for this answer are running now. SURF, the Sanford Underground Research Facility, occupies the old Homestake mine in Lead, South Dakota. The same shafts that Ray Davis descended to reach the 4,850-foot level are still there. The mine is still deep, still dark, still quiet in that particular underground way. But the tank of dry cleaning fluid is gone, replaced by a suite of modern experiments pursuing exactly these open questions. The place where the solar neutrino problem began is now one of the places where the next chapter is being written. Far from South Dakota, in Illinois, Fermilab, the Fermi National Accelerator Laboratory, named for the man who renamed Pauli's particle and whose paper on beta decay nature, once rejected as too remote from reality, is firing a beam of neutrinos northward into the ground. Aimed at a detector called NOVA at Ash River in Minnesota, 800 kilometres away, to measure the oscillation parameters with increasing precision. And deeper into the future, the DUNE experiment, the Deep Underground Neutrino experiment, part of the Long Baseline Neutrino Facility, will send an even more intense beam from Fermilab all the way to South Dakota, to a 40-kiloton detector filled with liquid argon buried in the same Homestake complex where Davis began. The experiment will look for CP violation, the asymmetry between how neutrinos and antineutrinos oscillate, which is precisely the ingredient that leptogenesis requires to explain the matter-antimatter imbalance. Enrico Fermi's name on the laboratory sending the beam. The Homestake mine receiving it. The loop is not quite closed, but it has a shape to it. And at the South Pole, beneath 2.5 kilometres of Antarctic ice, the Ice Cube Neutrino Observatory watches for high-energy neutrinos arriving from the farthest reaches of the cosmos, from the violent cores of distant galaxies, from supernovae, from places and processes we do not yet fully understand. It is run from the University of Wisconsin, Madison, and it uses a cubic kilometre of ancient glacial ice as its detector, woven through with thousands of sensors watching for the faint flash of Cherenkov light that marks a neutrino's rare encounter with a water molecule. The scale would have been incomprehensible to Davis, a cubic kilometre of detector, versus a tank the size of a swimming pool. And yet both are doing the same fundamental thing in their different ways. They are counting. So here is where we are. A particle proposed in a letter addressed to people Pauli did not visit in 1930 out of refusal to let conservation of energy go. Named by Fermi and theorists so well that Nature's editors thought the work could not be real. Caught at Savannah River by Cowan and Rains 26 years later in a detection Pauli had declared impossible and celebrated anyway with champagne. Measured in a mine in South Dakota for 30 years, quietly returning a number 1/3 of what was expected, patient as the rock around it. Vindicated twice by a Nobel Committee in 2002 and 2015. And vindicated in between by a tank of heavy water in Ontario that asked the question in 2 languages simultaneously. Electron neutrinos only, and all flavours at once, and found that the total was always right, and the electron count was always 1/3, and the gap between those 2 numbers was the 2/3 that Pauli's particle had hidden by changing its face. 65 billion solar neutrinos pass through every square centimetre of your body every second. Every second. Right now, as you lie still in the dark, the sun is sending its messengers through you, through the ceiling, through the floor, through the earth itself, which they traverse as if it were barely there. Most of them, 2/3 or more, are arriving as something other than what they started as. They transformed on the journey. They rotated through the quantum machinery of their own nature, the phases of their mass states drifting apart over 93 million miles until what emerged was a muon neutrino or a tau neutrino where an electron neutrino had set out. And they passed through a chlorine atom in a South Dakota tank without leaving the slightest mark, because a chlorine-37 nucleus cannot capture what they had become. They were never missing. They were always arriving, exactly on schedule, in exactly the numbers that John Bahcall predicted. The tank was always seeing exactly what it was physically capable of seeing. The chlorine was doing its job. The argon atoms were real. The counting was right. The deficit was real. And both of those things, the accuracy of the counting and the reality of the deficit, were simultaneously true, in the same way that 2 people can each be looking through a correct instrument at the same scene and each be seeing only part of it. For 30 years, the field leaned toward the quieter explanation. Not because physicists were foolish, they were not, they were rigorous and careful, but because the quieter explanation is almost always right. Assume the systematic error before you assume the broken law. Assume the model needs refinement before you assume the theory is incomplete. These are good instincts. They have served science well 1,000 times. But once in a while, rarely, the quieter explanation fails. Once in a while, the stubborn number on the page is not an accounting error, it is a message. The message from the mine in South Dakota was, "We are not massless." A particle you built your theory around, a particle the standard model described as exactly massless, is not. The phases shift. The flavours rotate. The conservation laws you built to describe how these things behave need a term you left out. The most successful theory in the history of science, the one that predicted the mass of the W and Z bosons to parts per million, the one that described the magnetic moment of the electron to 1 part in 10 trillion, the one that particle physicists sometimes call the triumph of the 20th century. That theory is incomplete. And the first place that incompleteness showed itself was not in a particle collider firing beams at energies no natural process achieves. It was in a tank of dry cleaning fluid. It was in a few dozen argon atoms extracted with helium every few weeks and counted, one by one, in a proportional counter barely bigger than your finger. It was in one man's careful, stubborn, decades-long measurement in a dark hole nearly a mile under a South Dakota gold mine. Ray Davis counted what he counted, and he was right. John Bahcall predicted what he predicted, and he was right. And the universe, quietly, patiently, without announcement, was doing something the theory had declared it could not do. Perhaps that is worth carrying into the dark with you tonight. Not as an unsettling thing, as a gentle and rather beautiful one. The most precise and successful theoretical framework ever assembled by human minds still has doors in it we have not opened. The neutrinos flying through you right now are not just carrying energy from the solar core, they are carrying that open question. That reminder that the account is not yet fully balanced. The mass ordering unknown. The Majorana question unanswered. The sterile neutrino neither confirmed nor ruled out. The CP violation in the neutrino sector not yet measured precisely enough to tell us whether it is the piece that explains why matter won. These are not failures. They are the shape of honest knowledge, a map where the known territory is drawn with extraordinary precision, and the edges, clearly marked, give way to the phrase that has always been the most honest thing science can say: we do not yet know. At the start of this long night together, I mentioned a man in a mine counting ghost atoms. A particle Pauli invented in desperation and then regretted. A deficit that ran for 30 years and was almost universally attributed to an error in the counting. And I suggested that the answer, when it finally came, was not that the counting was wrong or that the model was wrong, but that the universe was stranger than the theory had room for. That is still true, and I think it is one of the more comforting things about the kind of universe we live in. Strange enough to keep generating anomalies, patient enough to wait while we argue about them, and structured, underneath all the strangeness, by laws that turn out to be real and consistent and discoverable, in the end by people willing to climb down into the dark and count. Wherever you are tonight, whatever corner of the night holds you, whatever window shows you darkness or light, you have 65 billion of these things passing through you every second. You are transparent to them. And 2/3 of them are wearing a face that most of the instruments built to catch them simply cannot see. They are muon neutrinos and tau neutrinos now, converted on the long road from the sun, arriving punctually in exactly the numbers expected, passing through the planet. Passing through you, and continuing out the other side without a goodbye. The universe does not go missing. It just changes. If this slow journey through the mine and the model and the mystery helped you find some rest tonight, a like and a subscribe genuinely helps. Small creators like me rely on your support to keep these journeys going. And if you feel moved to leave a word, where are you listening from, and what time is it in your corner of the night? I always love to read those. Until the next voyage, sleep well, fellow voyager. The next journey keeps until you wake.